Hi, my name is Dong Luo. I'm gonna present DiffFit, a work done at KAUST in collaboration with INRIA. The molecular structure shown here in cartoon style in yellow and green can be simply regarded as a point cloud in our context. A cryo-EM map shown here as a gray isosurface can be regarded as a scalar volume. Fitting a molecular structure into a cryo-EM map is a common practice in the structural biology domain. The currently widely adopted method involves a manual placement followed by an automatic fine-tuning. With DiffFit, you probably notice we remove the need for manual placing, where it can fit within a few seconds. With the speed and accuracy of DiffFit, we can solve a complex and challenging task, that is, compositing smaller individual subunits into a larger volume. We basically turn this task into an automatic computing process, followed by an easy, user-friendly, interactive visualization analytics task. Bharti et al. Proposed Markov fit to use Markov random field to solve this problem. However, it involves multiple different command line tools, and it takes on average 14 hours to process one structure. They presented a benchmark table that we also use to profile the performance of DiffFit. As introduced in the beginning, in the domain go-to visualization tool CameraX, there is a functionality called fitting map. It requires manual initial placement. It does have a search mode, but it takes minutes to hours to search and occasionally fails to find a plausible fit. However, the manual fitting is still a routine practice, and the search mode has been used as a foundation in recent method and protocol papers. Gao et al. Proposed domain fit earlier this year to identify protein domains in cryo-EM maps. A core step, the fitting, is done by CameraX's fitting map command. Brantos et al. Proposed assembly line in 2022 to assemble small protein subunits into large cryo-EM maps. CameraX's fitting map command again serves as the foundational step in the beginning of their workflow. Our work is inspired by Reddy et al.'s differentiable compositing work, in which they developed a differentiable algorithm to composite pattern elements into a given final image. We first extended the algorithm to 3D and tested it on a toy example, which worked very well. But then the algorithm often falls into local minima for a long time for real cryo-EM maps, even though it might find the global minima eventually. We then adapted the algorithm to receive the atom coordinates or the point cloud as the input. We further enhanced the algorithm by introducing a few very effective strategies. The first one is adapted from Reddy et al.'s differentiable compositing paper, in which they generated a multi-resolution image pyramid for the reference image. This is to solve the problem that the gradients for optimization have a small region of influence. Extending this method to 3D will give us an iteratively convoluted volume array. Apart from give us a bigger region of influence for the gradients, it also happens to mitigate the noise inherent in the cryo-EM data. The second strategy is to fill the voxels that do not pass the threshold with a negative value. In CameraX's fitting map optimization algorithm, there is only a positive reward for the atoms occupying a density. With this negative space, we also add a negative punishment for the atoms that do not occupy a density. The third strategy is what we call enveloped initialization, to concentrate the search. Shown on the left is the sampling used by the CameraX fitting map command, which is sampling everywhere in the volume for an initial placement. In contrast, we sample only in the area that passes the threshold, as shown on the right. Now we introduce our loss function for the optimization algorithm. For a given volume, a set of molecular atomic models coordinates, we optimize the position and quaternion vectors by this loss function. It is the negative average of the density values sampled at the transformed coordinates. The transformation is done by a matrix converted from the quaternion vector Q and a translation by the position vector P. The sampling is performed by a trilinear interpolator. Then we get a weighted sum of all losses from the whole convoluted volume array for one molecule with one initial placement. We then compute on GPU in parallel for multiple placements in an ensemble style for one molecule. We further sum up all molecules' losses when there are multiple candidates to fit. With a target map, we fit a source structure with 1,000 initial placements. After the optimization, we get 1,000 final placements. If we instance a structure at each placement, we will get a highly cluttered and occluded view. After clustering and filtering, instances in two clusters then stand out. We then integrate DiffFit as a plugin into Camera X and build a tabular browser to go through the fitting results. The user can change the threshold to filter and cluster the results and click to check each cluster's best placement. We also build an interactive spatial viewer to get a spatial overview of all the clusters. Here we show the results of fitting a single structure, which is usually done in seconds on an RTX 4090 GPU. Here we show the benchmark of DiffFit. C stands for Camera X fitting map command, D stands for DiffFit, G stands for gain. You can see that DiffFit outperforms Camera X's significantly on both hit rate and computing time. In terms of fitting accuracy in root mean square deviation from the ground truth, DiffFit outperforms Markov fit to a large degree. DiffFit's accuracy is just slightly worse than Camera X's, and if the user takes the DiffFit's result as an initial pose and refine it by Camera X's fitting map command, then DiffFit gets a better accuracy. Here shows the process of compositing multiple structures into one cryo-EM map, which is usually done in minutes. Another breakthrough use case is to identify unknown densities from a large candidate library. This can be done in minutes to hours with DiffFit. The identified candidates are overlapped in the density. Comparing to domain fit, DiffFit gets about a 2-fold better hit rate and a 100-fold faster speed. One user expressed that DiffFit is quite intuitive and easy to use. The other mentioned the automatic fitting and visual inspection approach could be a key feature in Camera X that could become a standard in many pipelines, as well as a key implementation for a standard modeling workflow. We release DiffFit in two ways: a Python command line and a Camera X plugin. In the official marketplace, within 3 weeks of releasing, DiffFit already gets more than 500 downloads. We also fully open-sourced DiffFit. We are extending DiffFit to include a comprehensive visualization solution, deformable transformations, collision handling, splitting and splicing the cryo-EM map and structures. Many thanks to my co-authors, and thank you all for listening.